in-person event we've had since pre-COVID.
This meeting is being recorded.
Oh, let me start again. Welcome to the Reinforcement Learning Forum. This is the first in-person event we've had since pre-COVID. And man, it's nice to see people in physical form. So it's so good to see everyone here. Makes it much more fun. It's really amazing to have Ian here because Ian started the Reinforcement Learning Forum along with Dan Russo about 10 years ago, probably before reinforcement learning became a mainstream topic. It was a bit of a fringe activity back then. And he was a PhD student at the time. And while a PhD student, he really pioneered the use of principled approaches to exploration in deep reinforcement learning. And he worked on that here as a student. He did an internship at DeepMind, which had just been acquired by Google at that time. And he's since then continued driving this agenda at DeepMind. And really central to all of that has been approaches to estimating uncertainty. And those approaches have matured over time. And what he'll talk about today is a subject of epistemic neural networks, which represents a mature version of that line of work. And I think it's at a point now where he's positioned it to be really useful across a broad range of applications in deep learning, in reinforcement learning, and beyond. So we're excited to have you here, Ian, and look forward to your talk.
Great. Thanks a lot, Ben. And yeah, thanks to everyone for coming out today. It's really, yeah, as Ben said, it's kind of full circle. And I guess if you set up the thing, then that's a privilege to get to come back. And so thanks a lot. Obviously, this is, I'm here talking, but this is the culmination of a lot of people's work. Certainly Ben driving a lot of this agenda. And, a few of those people are tuned in on the Zoom feed. But I'm really excited to talk to you about it. And this is work with the Efficient Agent team, which is a DeepMind group in Mountain View that we've really got started over the last year. And thanks to Grace for coming out, who's going to be joining us in September. So we're all pretty excited. Feel like we're making great progress. Well, I guess, I don't want to be too embarrassing about this AGI stuff, but I think we are driven by this really, big picture goal and, AI, AGI, and we think we need uncertainty in that. And you need uncertainty for tasks like exploration, which is about seeking out new data to get new information. Adaptation, when you get new data, what information should you extract from that data? And decision making. When you have a given information state, what action should you take? And in all three of these situations, it's important to know what you know and also know what you don't know. And neural networks, as they're currently used, don't know what they don't know. So deep learning has obviously, been at the heart of progress in machine learning over the last, decade. But it's kind of still a grand challenge for AI, how to work out how to get good uncertainty estimates in deep learning. And here I'm reusing a slide from Balaji's tutorial on uncertainty in deep learning. And really the goal is talking about this uncertainty and robustness frontier, which has typically been studied in Bayesian deep learning. And in Bayesian deep learning, you have a prior, you have a posterior over weights, and that handles your uncertainty. And kind of it's a well-formed problem, and asymptotically in compute, you know what the answer is, or we know that there are ways that can do it, MCMC. But in practice, that's too much compute for large deep neural networks. And so there are these other trade-offs like variational inference, ensembles, dropout, lots of different things. And the picture on the right really highlights the statistical versus computational trade-off. So the idea is you have a single neural network. Well, that doesn't have a very good quality of statistical uncertainty or robustness, but it's kind of cheaper in terms of compute. And on the other end, there are these Bayesian neural networks, large ensembles, that are somehow better in uncertainty and robustness, but cost a lot more. And part of the name of the game is balancing the statistical and computational trade-offs in the design of, efficient agents. But in this talk, in just to give credit, this is a team at Google Brain working with a lot of people at Oxford and, really kind of, I guess, thought leaders in Bayesian deep learning. And in this talk, provocatively, we're going to tell you something that's much, much better than these trade-offs, right? That kind of goes outside the box and is doing better statistical quality than very large ensembles, but at computational cost that's only slightly more than a single neural network, okay? And kind of the way we're saying is that we're able to do this through a kind of paradigm shift, through looking at the problem in a slightly different way. And this is not meant to explain what we're doing, but it's meant to get you excited, or to think, hey man, this guy's talking nonsense, I'm going to poke holes in it, and please do. But this is what I'm promising you, and hopefully by the end of the talk you'll be convinced. So what's this talk going to do? Well, first is we're going to introduce the epistemic neural network. So that's a neural network that knows what it doesn't know. So it's a lot like Bayesian neural networks, but rather than focusing on unknown weights, we're really going to focus on predictions. And we're going to give you a new way of thinking about that in terms of joint predictions. We're going to introduce the Epinet. Epinet is a new type of ENN, epistemic neural network. And it basically, you start with a base model. So for example, a big ResNet or something like that. And then you add on a little bit of an extra neural network that's somehow going to give you uncertainty estimates, okay? And basically, we're going to call these kind of moonshot results, is that using an Epinet, you can do better than a size 100 ensemble, but at much less than 2x compute, right? So neural network plus Epinet, only a little bit more compute, but it's better than a really large ensemble. We're going to show you a progression from simple examples to Imagenet and even RL. And so hopefully we can deliver on this, or hopefully it get you excited. And out of these, probably the most exciting are the results. So let's start there. Or obviously link you to, there is a paper on arXiv and a few other things. But let's start with these results. So I said, hey, we can do better than ensemble size 100 at less than 2x compute. So let's just start there. Well, firstly, I want to talk about neural networks don't know what they don't know. And I'm going to show you two pictures of, imagine a neural network trained to classify if an image, a random person would call this a rabbit or a duck. Those are your only two choices, rabbit or duck. And neural networks, typically you get one image in and you have a probability distribution out. And case A, it's kind of obviously that it's a rabbit, but this neural network says, hey, 50-50. And the reason it says 50-50 in this example, I would say, is because it has insufficient training data. Because if I asked any of you here, you'd all say, hey, this is a rabbit. This truly is a rabbit drawing, right? It's not a duck. And people call this epistemic uncertainty. Epistemic means to do with knowledge, okay? And that's type A. But this drawing here, rabbit and duck, it's a famous illusion. If you look at it one way, it's a rabbit. If you look at it another way, it's a duck, and hopefully people can see that here. And the idea is that, hey, this is genuinely ambiguous image, right? It really is something that's 50-50. But in this neural network interface, right, just think about it from a coding, you give me one image, I give you one probability, right? There's no difference, right, between this 50-50. There's no space in this interface to tell you the difference between A or B, right? It's something neural networks don't do, right? Now, I guess maybe I'm making a leap here, but it's useful to be able to tell the difference, right? It's useful to be able to tell, hey, is this something that's genuinely ambiguous, or is this something which I need to learn about, right? And if you can't even tell those things apart in this situation, well, you shouldn't be using this type of interface, right? And I guess what I'm going to show you here is that this idea of joint predictions. So if instead of asking you, hey, one image, one prediction, I'm now going to give you the image twice, right? You got two copies of the image and I give it to two random people. I now pass it to an epistemic neural network. I'll tell you what that is in a second. But an epistemic neural network is a special type that can make joint predictions. And so a joint prediction means instead of it being a, just two options, there are now four. It's 2 by 2, right? And it's the joint predictions over, are these, not is each image a rabbit or a duck, but are these two jointly rabbits or ducks or rabbit and duck, right? So the distribution over all possible outcomes, you can have rabbit, 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 duck, duck, rabbit, duck, duck. Now, the thing that you called aleatoric, the thing of random chance, this is truly something that, hey, you give it to a random person, it's 50-50. Well, then all four outcomes are equal, right? And that's shown by each having a quarter in each of these four outcomes. But the thing which we called epistemic can be expressed by this joint outcome. They're either both rabbits or they're both ducks. Okay? And so suddenly, by looking at joint predictions, this thing that you had no way of telling apart, what was it, epistemic or aleatoric, or is this something you don't know versus something that's just ambiguous, you can now tell them apart, right? But there's something important about this, is because actually, I put epistemic and aleatoric in inverted commas, because that's something that's actually internal to a model, right? If you have an agent that has a linear model, you know, then you could say, hey, I'm Bayesian with this prior or these weights, this part's epistemic, this part's aleatoric. But it's kind of subjective to that's only from the perspective, for a given model, you can say what's epistemic and what's aleatoric, but it's not real. It's not a real part of the data. The only thing that's real is what you observe in the actual data, okay? And so while you can evaluate epistemic versus aleatoric quality for a fixed model, you can always evaluate joint predictions for any model. And the best ones are the ones that just make the best joint predictions. It's kind of an objective measure of quality. And really, a kind of a surprising thing that's come out from this agenda over the past year is that it's actually the quality of joint predictions that drives decisions. So on the right, I've just got a scatter plot observed of a bunch of agents that we evaluate the quality of predictions they make on the x-axis, and the performance, with lower being better. Lower is better on both the x and the y. And if you only look at the marginal predictions, there's no correlation. But if you look at joint predictions, there's a strong correlation. But I'm just going to cite some papers here. We've got one which is basically based on theory, that's saying in order to make good decisions, you need to have good joint predictions. The second paper is an empirical testbed for evaluating this in deep learning. And the third one is about scaling this to higher dimensions. And so I'm not going to talk about these, but basically one of the premises, and I'll show you some other results, but the idea is that, hey, joint predictions are actually really important. And people don't talk about them a lot, you know, in image classification or stuff like that. So it's kind of been a blind spot, I think, in the deep learning community. So with that, now I'm going to show you these results that I think are really exciting. And they take a while to go through, but it's going to be worthwhile and hopefully get people fired up. So first we look at Imagenet, and we look at 3 measures of quality as we vary model size of ResNet 50, 101, 150, 200. Okay. And on the x-axis, we have the model size. And on the y-axis, we have the statistical loss. And we have 3 different plots because we have 3 different notions of performance. The first plot is classification error, right? And as you can see, bigger models do better. People know this, right? Scaling laws, bigger ResNets do better. So lower classification error. The next one is marginal log loss. So that's looking at a single image and seeing, you know, the quality of the predictions. And the final one is joint log loss. So this is a special way we get basically a batch of a few different images, and some are similar and some are different. And how do you do well jointly over that batch of image together? Okay. Now, in all of these, ResNets do better, right? Bigger ResNets better, bigger model better. The next benchmark we're going to do is an ensemble of ResNet 50s. So this is a plot. The x-axis is a log scale. So this is 1 ResNet, 3 ResNets, 10 ResNets, 30, and 100. And as you can see, as you view this ensemble as a bigger models again do better, right? And, you know, so an ensemble does better than a single model, but for a given amount of budget, actually in terms of classification error, you do better with a bigger model. That's not that surprising, right? Because we know GPT-3 is not an ensemble of GPT-2, right? And in marginal log loss, okay, it's kind of the same, but there's something interesting here. So in terms of joint log loss, which is somehow related to epistemic uncertainty, the ensemble actually does better, like for like, right? And that's because ensembles, you know, through the variation in these can model this joint predictions, right? And so it actually does do better than a bigger ResNet. Yeah.
So sorry, it keeps coming up, so I'd rather ask right now, but when you say joint prediction,
yeah,
so far the only image I have in my mind is feeding the same sample twice as you did in
yeah,
the
yeah.
example. Is that exactly what it means, or does it mean predicting over a set of samples?
Yeah, set of samples, but some of them could be the same or similar, and some of them could be different. And in fact, some of them, that's important. That is how we evaluate it. But basically, imagine you get a batch of 10 images that are coming in, and let's say some of them are of this one class and some of them are the other class.
Okay.
Yeah. Yeah, thanks for the question. And so the last thing we've got is this Epinet approach, right? And so Epinet is a ResNet plus a small extranet, okay? And look, it doesn't really improve things much in the classification error. It doesn't really improve things that much in the log loss, right? It's about the same, but it's only a little bit extra compute. But in terms of joint, we do far, far better, right? And so this is what I'm saying is the kind of the moonshot, you know, exciting result, okay? Now, I think the question you might have is, hey, do I really care about joint, right? Well, do I really care about that? Okay, well, hopefully we can go into that and we can talk about that a bit more. But what I think I'll say is, yes, you should care about that because it's the quality of joint predictions that's useful for driving decision making, right? And basically this Epinet and this approach is able to do much, much better than even very large ensembles, which are viewed as state of the art, right? But at cost only slightly more than a single model, right? So this is the best result. This is the main, you know, the headline plot. It takes a while to walk it through, but this is what we're going to kind of work up to, back up to in the rest of the talk. A few other things, but this is the main result. Cool. All right. Oh, sorry. And we have a few other results. So we run it on this neural testbed, which is the synthetic problem with random MLPs. We run it on bandit problems, which is also generated by random MLPs, and also in a reinforcement learning task. And these plots are too small. I'll go through them later. But in each of these, it's an x-axis is compute, y-axis is performance. And in each of these, I've highlighted this Epinet, right? And somehow this Epinet is able to balance statistical quality against computational cost better than the other approaches, right? So it's kind of consistent across all the tasks. And it's, you know, the same approach we're using in all of them. So with that, hopefully you guys are actually excited to learn about epistemic neural networks and the general approach. And it's neural networks that know what they don't know. Okay. So what's an epistemic neural network? Well, I'm gonna, you know, these network diagrams, I think it splits opinion. Do you like them? Do you hate them? But let's say we start off with a conventional neural network, takes in an input, X, has parameters theta, and predicts outputs. And an epistemic neural network looks pretty much the same, except there's this additional thing called the index. And the index is a latent variable. So if you want to think concretely, it could be something like a 10-dimensional Gaussian, standard Gaussian, that the agent, the network generates according to some reference distribution, and it uses this while it makes predictions. Now this reference distribution has nothing to do with the real world, but it's kind of a latent variable that you can set up that the neural network can use to model its own uncertainty. And where is this important? It's the joint prediction problem. So we'll get through this. So I'm asking the question, hey, I'm going to give you inputs x1 to x tau, predict labels y1 to y tau. What does a neural network do? Well, a conventional neural network, let's say it's classification, is you take the softmax to get the probabilities for each of the inputs, you look at the component yt for that, and you multiply them together, because neural networks are made for marginal predictions, right? So when you do joint, you get the product of the marginals. What does an epistemic neural network do? You integrate over this reference distribution the product of the predictions for each index z. So an epistemic neural network takes in the index z, but when you make joint predictions, use the same z across multiple predictions. So depending on the structure of this neural network, the joint prediction is not exactly the same as the product of marginals. And it's through this mechanism that we say an ENN can know what it doesn't know. Okay. So this is worth pausing on a little bit. So this is really it. It's like, hey, neural networks are set up to do marginal prediction, and ENN is a mechanism by which you can do joint predictions. Now, just setting it up like this doesn't mean it's going to do good joint predictions. We'll have to say how to do that later. But at least it should be obvious, like if you want to be able to make predictions that aren't just products of marginals, right? The original neural network couldn't do that, right? And this approach can do that, because this integral over the z can couple the predictions from x1 to x tau. Now, things you already know are ENNs, right? It's a different way of looking at things, but the deep ensemble, right? You've heard of ensemble of neural networks. Well, you can view this as an ENN. So the ensemble, you've got weights, 1 to k particles. We can view this as an ENN where the index is uniform over 1 to k. And when you forward it, you pick one of them and you do it, right? Dropout as approximation. You can view it as index z is the dropout mask, right? And when you forward, you take the weights and you dot it with the mask, right? Bayes by backprop. So in Bayes by backprop, you have a mean and a standard deviation for each weight. And you can say that the index z is a standard normal. And your prediction is just mean mu plus sigma, dotted with this z, okay? So no one talked about it like this before, but these are, all the things you exist, you can write them as ENNs. Now, what people did talk about before was Bayesian deep learning. And I think there's a big connection, right? So Bayesian neural nets are ENNs, okay? A Bayesian neural network is when you have a posterior distribution over the weights of your neural network, okay? And they break it down into two pieces. You have epistemic uncertainty over the weights, and then aleatoric. So epistemic is due to knowledge. You have that over your weights. And aleatoric is due to chance. And you have that over the outputs, okay? And, if we rewrite this theta as some function of the index, it should be obvious you can express this as an ENN. But not all ENNs are BNNs, right? Because we didn't say that this index has to resolve the weights first and then make your prediction. It's just, hey, you make predictions using this index. So Bayesian neural networks focus on learning these unknown weights, and ENNs just focus on making joint predictions. So you can do it by making a Bayesian neural network, but you don't have to, right? And I think, okay, I guess the idea is that by saying, hey, if all you care about is predictions, well, unshackle yourself. You don't need to have those restrictions that might be holding you back. It's an easier problem. You just do good joint predictions. Maybe that's all you need. Okay, so with that, we go to Epinet. So Epinet is a new ENN architecture that isn't a Bayesian neural network that we say does better. So what is that? So the idea is we're going to make this ENN, so this notation, f theta of x and z, and we're going to break up the parameters theta into two separate parts. The zeta, which is just a base network that doesn't depend on the z, the index. So it's just basically think your standard neural network. And plus this extra piece that is going to depend on these features x tilde, I'll say what those are in a second, and these other parameters, and does depend on z. I've got a drawing here that kind of visualize it. The idea is you have your input x, goes into your base network. This is somehow going to expose high-level features, which can include the original input, but also hidden representations. And then that plus the index goes into the Epinet. When you add them together, you get an output. And so to line up these boxes, that's the blue part, that's the red part. Okay. So it's an ENN you add to the base network to make the combination a good ENN. What's the idea? The idea is, hey, if you've invested loads of computation and learning in like making a ResNet 50, well, maybe those hidden units are useful for predicting, your uncertainty, right? Or we can just use standard neural network pieces that we know work or empirically work, right? ReLU activations, certain initializations, SGD training. Whenever you try to mess with stuff and, do hypermodel this or Bayesian learning, it's hard to tune, but we're going to use the things that just empirically work and try to set it up. So I don't know, does this look something like a Laplace approximation? That's why we got the mu and the sigma. The idea is, hey, you got a mean part and then a little bit extra for your uncertainty. But this is the idea and this is the algorithm. Okay, now how do you set this up to work? Well, one of the key ideas is this thing called randomized prior functions, which is, I guess, a paper we wrote a while ago for getting a prior effect into ensembles. But the idea is that if you want to train some predictions, f of x and z, you can break it up into some piece with no parameters that you sample from the prior, like a prior belief, and then you add a little bit of trainable network on top of it. And I've got a picture here from that paper. And again, this is going to be one of those things where I try to go a bit slowly and try to, it's worth going through. But in each of these plots, there are 4 plots, I show the effects of training a neural network, a ReLU neural network, on the same data points. So the data points, x and y, are the dots. And the part in blue is the prior function. It's a different prior function for each of these. So this one has prior 0, p of x is 0. This one has p of x as some sign. This is some, like that. This one exponential. Then you add a trainable network. So that's the dashed lines. And we're just going to train this with SGD so that the resultant prediction in red goes through all the points, right? So initialize the algorithm simple. You sample, and this is Z1. You can to connect these to different index. This is an ensemble. So they're separate, Z1, Z2, Z3, Z4. In this one, you're training the neural network to just go through all of these points. And this is what you get, right? And you can say, hey, the red line kind of goes flat on each end. In this one, you're training the dashed line so that the dashed line plus the blue part goes through the points. And it does go through all the points, right? But it extrapolates in different ways, right? It goes up here and down there. This one, it's a different prior, so you get different extrapolations, okay? But all the samples, these are viewed as like approximate posterior samples. They all agree on the training data, right? But they generalize differently depending on the effects of the prior and the learned network, okay? And in some situations, if you set it up right and you do it, linear this, Gaussian that, you can actually get this to do exact Bayes inference. But in general, it's more of a heuristic that you can kind of tune, hey, this type of prior structure, that type of network, right? And we can get some kind of effect, right? So this is kind of the key thing. If you follow that link, there's a Colab, you can play with it. You don't need to install anything. But this is the idea. You're going to have different random offsets for different Z's. And this will give you an effect, something like a prior. So when we make our Epinet, we actually have that effect. We have the base network and we have the Epinet, but it has 2 separate pieces. One is this prior network that has no parameters, but is initialized such that initially the variation in Z reflects your prior uncertainty. Okay, the index Z. And so that after training, the resultant variation in Z is meant to be something like a posterior. And this is the drawing of the full network. So showing the parameters, showing the features, what depends on what. Yeah.
This is very cool. You might have said this, but what was the reason for having that additional prior term? Like, well, why couldn't you, like,
Yeah. Okay, that's great. Thanks for asking the question. So basically, the worry is if you didn't set up the, well, I haven't said what the loss function is, and maybe that's going to be the next thing. But if we didn't have the prior function, we're going to train it on data X and Y, right? And we train it on real data, but the Z really has no effect in the real world. And so if you didn't, what would stop the neural net? Why should the neural network pay any attention to this thing Z, right? Why is it helpful to use that? And the reason is because you want to set up that there's, hey, and if I drew this, imagine if I trained an ensemble, because this is an ensemble of size 4, right? And when you look at the predictions, imagine going out to the right, this one says goes middle, this one says down, this one says down, this one says up. And when you look at them all together, it says, hey, I'm uncertain about what happens to the right. Imagine if I trained this with multiple seeds, right? Well, maybe they'd all kind of, yeah, one would go slightly up, one would go slightly down, right? But it's giving me something like a prior effect that I can tune, right? Apart from just random initializations. And so that's really the point is that, hey, this gives me something like a prior knob that I can tune apart from just random initializations. Oh, okay. Going to the train, how do we train this Epinet? Well, it's actually basically just the same as a standard neural network, but we the loss, so it's a loss that depends on the parameters and the data, right? And this is just meant to be a loss summed over the data and some regularization. The only thing that's weird here is we've got this Z in here, right? That's not there for a standard neural network. And we just say, hey, integrate that over the Z on average. You should do well on average, right? This is something that you control. And if you want to train it, we do the usual thing of like, hey, when this is the ideal loss over the whole data set, but you sample a mini batch, right? And just like you sample a mini batch of data, we're going to sample a mini batch of Z's, right? So that means you sample a few index and you take SGD with respect to that. Okay, and what are our losses? So we've got two terms here. We've got a data loss and a regularization. We use the normal, the usual stuff, right? So for regression, we use mean squared error. So that means you take the output, which depends on Z, right? And mean squared error. Classification, we use, log loss. So work out the probability, take the log of that, right? And the component Y. Regularization, we just do the L2 on the weight decay, on the weight, right? So this is meant to be, and I think probably there are better ways, right? And look, there are better, more advanced training, but all the results I'm going to show you are just using the standard training algorithms, right? Do this with SGD, with Atom, right? The usual softmax. So that's a bonus as well, right? Because you're just reusing the standard stuff. Yes.
So if I understand correctly, it seems like the Z is about grabbing batches from dipping into the bag of samples, right? With some distributional properties and a number of them too.
The Z things?
Yeah.
Yeah, the Z, so I'll make it concrete. The Z, think Z is a 10-dimensional standard Gaussian that you feed into your neural network. And when you make predictions within ENN, you have to give it the input X and the epistemic index Z. And so when you sample a batch of data and you want to train on that, you have to say, hey, which indices am I going to train on? So you sample a few random ones and you train on that.
And then when you integrate over the distribution of Z, there's a bootstrap feeding about it, which is essentially I'm taking a bunch of sample or batches according to Z, and doing it multiple times.
Yes.
And the size of the batch is almost like the bootstrap size.
Yes.
And the repetition is as if is.
Yeah, I think so. I think it's similar to that. You can actually, we have some versions where we actually use this to do statistical bootstrapping as well. But I think the thing I'm proposing here is just like a sample-based average right now. That's the main thing. But you can totally do the more bootstrapping stuff as well. But yeah, so it's just like, hey, I'm just replacing this integral, which I do, with just a few samples. But yeah, thanks for the question. Okay, what are some useful properties? It's probably got to speed up a bit. But anyway, we can make this exact in linear regression if we do this bootstrap loss, as you say. If you want multiple samples, you only need to forward the base network once. So imagine base network really, really big. Epinet can be quite small, right? So you can do 1,000 samples or something like that, quite cheap. It's a nice fit for pre-trained models, right? You download GPT-3, you do a little bit of Epinet on top of it, hey presto, you get uncertainty estimates. And I think it's a new perspective where we're reusing existing blocks that we know actually work, right? So that's good because you kind of can use the deep learning like hacker community to work for you instead of working against you. Like neural networks work really well, and that makes Bayesian deep learning kind of hard, right? Because they're confusing, you don't really know how it works. But we're hoping that'll make epistemic neural networks really easy because they work really well. And I don't really understand why they work, but hey, I'm not going to complain. Right? So I'm going to accelerate a bit, but we're going to got these supervised learning results. We'll review them again. We start with saying neural testbed. Neural testbed is basically simple problems generated by a 2-layer ReLU MLP. So that's an example on the right. You've got training data. It's a 2D problem. You've got training data in the dots, and it's color-coded by the class. And the network's going to train on the training data, which is the dots, and it's going to be evaluated in terms of its quality of predictions on random testing data. But because it's a generative model, we can do this, many different seeds, lots of different scenarios, and it's just a sanity check. It's open source. And what is this Epinet that we use? Well, here I've got an 8-dimensional, and we have ablations and stuff of what's important. A lot of these things aren't super important, but we've got an 8-dimensional, why is it 8? I think it's because we were trying to make it as small as possible while still getting as good results as SGM-CMC. We have an 8-dimensional Gaussian. The features that go into the Epinet are the input X and the last hidden layer from the original network, concatenated. And we do an MLP that goes to 2, because it's 2 classes, times DZ, which is 8. And we dot that with the index Z. So I could draw it on a whiteboard. It's not super important, but the code's there, it's open source. But basically, you've got a neural network that goes forward, MLP, you take a dot product with the Z. That's your prediction. Why did we pick that? I think mostly just one of the first things we tried, and kind of by comparison to a hypermodel. But I think, that's what we did. And what did we use for this prior thing? Well, we had some very small MLPs and an ensemble of them, which get dot product, an ensemble of 8 of them, DZ, which also get dot producted with the index. Compare this against a bunch of other agents, right? And so we got MLP, ensemble, dropout, BBB, hypermodel, ensemble plus, SGM-CMC. That's kind of the gold standard. That one uses way more compute, right? And here's the performance, right? And again, it looks a bit different, but it's the same plot we had before. We've got the compute on the x-axis. We've got the statistical loss on the y-axis. We've got the classification error. We've got the marginal log loss. We got the joint log loss. And really, after tuning all of these things, they do pretty similarly in the classification error. Some things do better in marginal log loss. That's the SGM-CMC. That is better. That's the best agent, right? Uses just way more compute, like thousands of times more. And in terms of joint log loss, well, some models are really good, like some are pretty good, and some are not that good, like dropout, whatever. On this ensemble, BBB, they're not very good, right? But Epinet, again, kind of as we had before, is somehow performing as well as the really expensive models, but much, much cheaper, right? And this is just a really simple setting where you should be able to, we know what the optimal thing is, and the SGM-CMC can get it, but we're able to do similarly, but just much cheaper. And so now we're back to Imagenet, and what's Imagenet? So it's a classic benchmark. We train these baseline ResNets. And so these are the results we're having before. The index, we've got a 30-dimensional index. The features that go into the Epinet are just the last layer from the pre-trained ResNet. Oh, I didn't mention, well, I'll mention this in a second, but actually we didn't even update the weights of the ResNet after training. We just took those and held those fixed, and we only trained the Epinet weights. I think you could do even better if you fine-tune the ResNet as well. So what is the learnable part of the network? We've just got it's an MLP that goes from, it's similar to the thing we had for the testbed. It goes from the final hidden layer to 50 hidden units to 1000 by DZ, which is 30, and then that gets dotted with the Z. That's the learnable part of the network. So it's just got this kind of nonlinear MLP form. We have two priors, or the prior is made up of 1 plus 2. So we have this one prior, which we call like a feature prior, which is just the same as the learnable part, but with a different random initialization. And the prior 2 is an ensemble of a very small convnet that goes directly on the images, right? And we call this a pixel prior. But what are these saying at high level? It's like, hey, images that have similar hidden features should be similar. Images that have different hidden features should be different, right? That's all it's really saying. It's not a very strong prior. But we have this in a collab. You go into this, you click into it, you can get the pre-trained weights, and you can just have a look at all of them, and you can run it, right, really quickly, right? So it's pretty cool. And so you've seen this plot before, but hopefully now, you feel like you've earned it. The same thing. You're going through ensembles, and you know where this is going. We're much, much better, right, in terms of the joint predictions, right?
Quick question. So if you take these pre-trained models like a ResNet,
yeah,
basically the architecture is such that you can take in one image and
yeah,
produce one distribution, right?
Yes.
It's not clear to me what the changes such that, I guess for your joint tasks, you have a fixed number of samples you feed in at the same time, right?
Yeah, exactly. So so here, and we've got this thing. So we're gonna have a batch of images, right? And for each of those images, the base network only gets forwarded once, but the Epinet gets forwarded with multiple samples, right?
So I guess if you permute the samples,
yeah,
you don't have the guarantee that you will get the same permuted joint distribution.
I think you do if you do it the right way. It will be the same. If you have the same Z's and stuff, it will be the same.
So,
yeah.
So that's why these are called indices.
Yeah,
okay,
exactly.
Okay, got it.
But yeah, that's a great question, and yeah. So the kind of the important thing is that we're going to forward the base network once. That's expensive. The Epinet's quite cheap by comparison. Forward that lots of times, right? And yeah. Now we did the same results. We ran the same thing. Did not tune this. Ran the same thing out the box on CFAR 10. Pretty much the same picture. Slightly smaller ResNets and CFAR 100. And when I say it's basically the same, it's that, hey, look, in terms of classification, marginal log loss, things are much of a muchness, but we're much, much better in joint log loss, right? And that's good because it shows that this is somewhat robust. It's not like super tuned to Imagenet. So there's kind of a consistent pattern happening here. So with that, I guess we move to reinforcement learning, the last few things. And that the overall is that better predictions lead to better decisions. So we're thinking of, and reinforcement learning, don't need to give a review of this here, but the agent interacting with the environment. We basically are going to take a DQN benchmark, which uses an action value function with a neural network, and we just replace that with an ENN for the action value function. So it's the same as before, but we just say, hey, you have this index Z, right? This is a formalism. What we're actually going to use is the same Epinet and same other ENNs from the neural testbed, the thing that was made to work with simple 2D things. We use those exact ENNs. Now we look at them in decision making. And we do action selection via Thompson sampling. So how do you implement that here? It means you sample an index once at the beginning of an episode, and you hold that fixed for that episode. And so this is an instance of deep exploration via randomized value functions. And so, you know, yeah, title of my PhD dissertation, but you know, go check that out. But yeah, when you put it out like this, it's pretty simple, right? So I don't know, how do you do a whole PhD on that? I don't know. Yeah, come in, yeah. Yeah.
In this context, Z is selecting in the state space or also the action space?
It's kind of interacting with both. So basically in DQN, you typically have a function that goes from, I guess, state or observation to action values. And with an ENN, that you need to go from state and index to action values, right? And so you need to say, how do you select this index on each episode? And the way that the algorithm goes is at the start of this episode, I flip a coin. This is my index. And now I'm going to keep that fixed for the full period. And so I guess for a fixed ZK, you're back to just having a standard neural network. And it looks like the original DQN thing. So we make this thing of bandit problems from the neural testbed. So this means that there are, it's a 100-dimensional problem. There are 1,000 different actions, and the rewards are determined by this random MLP. And we're going to compare the agents varying the choice of ENN. And the choice of ENN makes a big difference. And so that's what's shown on the right. It's the average regret through time of these different approaches. From worst, it's just the standard MLP. You get better with these different ensemble dropout hypermodel. We couldn't run SGM-CMC, it was too expensive, but Epinet is best, right? It does actually better than all the others. But the cool thing is that this is high, you know, it may just seem like a pretty random, hey, how do I know which one is going to be best? Well, this is pretty cool. So here I've got plots. On the left, I'm just showing, on the x-axis, I've got the KL loss on the testbed, prediction quality. And on the y-axis, I've got the regret. And I've got run with a bunch of different seeds and use bootstrapping and try to look at the correlation. And basically, no correlation with marginal KL loss. Pretty strong correlation with the quality of the joint KL loss. So the agents that are doing better at joint prediction tend to also do better in this decision making. And Epinet is beating the large ensembles, right? So that's great. So this is a simple RL problem, but you know, it's, if you can't solve this, hey, what can you do? We then run this thing B suite, which is, I guess, a benchmark suite. It's called behavior suite, meant to highlight key issues in RL. And the generative model is not an MLP. These are just tasks which certain researchers have curated and said, hey, this is an important challenge. It's very difficult exploration or very difficult credit assignment, something like this. And on the right, you can see the kind of performance characteristics, and I just highlighted 3. One is this ensemble plus, the ensemble plus prior functions, and Epinet basically does as well as that, right? They're very similar, you know, don't have error bars here, but basically the same. And yeah, it's doing a little bit worse on the scaling, you know, versus MLP, but so is the ensemble, you know, let's look into that a bit later. But once again, varying the ENN makes a big difference. And there's, again, a really high correlation with the joint prediction. So I'm just going to show you the same plot as before. And it looks almost the same, right? I mean, they're kind of more clustered, but it's like agents that do well in joint prediction are the ones that do well in decision making, right? And the Epinet is able to match large ensembles. Right? So maybe now you're kind of saying, hey, well, maybe I really do care about this joint prediction. Hey, it's a bit of a weird thing, but turns out, you know, this seems to be able to use it in decision making. And I think that's really what we hope from this. So with that, what next? You know, now I'm going to really wax lyrical, you know, go full, you know, DeepMind or AGI with an ENN inside. So right now, what are we doing right now? Well, we're working on a few projects with robustness and OOD. And I think the answer is that using an Epinet helps. It doesn't completely solve the problem, but it helps. It's better than ensembles or other approaches in some of the, you know, Imagenet A, Imagenet C, Imagenet O. We're doing some work on large language models. Can we add uncertainty to that, right? And another one is, you know, trying to make a better version of these mu0 ++. Hey, can we get deep exploration in mu0. In the last 5 minutes, we're going into the future, hey, if a neural network is plausible in the brain, well, why not ENN, right? And there are some people, this was the classic, you Google trying to find the answer you want, but some people are saying, hey, the neural network noise shows the uncertainty of our memory. Well, there's not much to an ENN apart from that, right? So if that's possible, why not say it? We need Jeff Hinton to argue it though. Science, I think there's lots of problems where joint predictions are important. And, maybe as we build towards, intelligent agents, they got to have a knowledge representation. And if you want to do exploration, generalization, all these things, multimodal, credit assignment, continual learning, well, deep learning has really been at the heart of all this progress, right? But that's using neural networks. And after this talk, you don't want to be caught dead with just a normal neural network. You want to have an ENN inside. So you heard it here first. This is your chance to get ahead. So, okay, we've got open source software actually. And so this is really how you can get ahead. Yeah, we've got 3 libraries. We've got ENN, which has architectures, loss functions, training. We've got this neural testbed, showed you those results. And we've got this ENN Acme. So you can have RL agents that use these. So each of these has starter collabs. You can just get going, I can't promise, it's not going to be, look, message me if you have any issues, but I think you can at least get going on that. And it's pretty good stuff. So please, go ahead and use it for your project. And I really think there's a lot more you can do, right, to make these things better. I told some of our team members, it wants to work. Sometimes you tune things and nothing ever works. This seems like it, kind of wants to work. And so I'll be excited to see what people can do with it. So summary, we set this internally as a moonshot goal. Hey, can I be better than a big ensemble at less than 2x compute? And if you're really eagle-eyed, you'll be like, hey, you did kind of change the metric to this joint thing that no one really wanted. But so we did do that, but actually the joint thing's really important, and I think it's really exciting. Epinet, I think, is really promising technology. I think it's really awesome that you can do things with these pre-trained models. And that's just exactly what you want, right? And I think the ENN perspective could be a useful building block in AI development. It's so similar to the neural network stuff, but the fact, once you realize, hey, neural networks can't do joint prediction, you have to be able to do joint prediction, right? So ENN seems like a no-brainer. There's obviously a huge amount of related work. I tried to cite some of it, but there's plenty more. And I think limitations, as I said, this joint NLL is kind of a proxy metric, right? No one woke up, hey, what's my big challenge? I want to do joint predictions, right? But I think it's going to be something that unlocks other things that people really do care about. I think we have, state-of-the-art scale. If you wind the clock back to 2016, ResNet 50 used to be really impressive, and now not so much. I think we're looking as a team, we're based here, so collaborators and collaborations are definitely on the cards. And I think right now it's more of a vision than the real results, right? The really exciting stuff I think is still to come. But I think it's got a good chance of working out. So excited to hear any questions. Thank you. Go ahead. Yeah.
Yeah. Okay. Sorry again. So you said ENNs know what they don't know, and I guess with the first example that you used, where you're sending in the same sample twice,
yeah,
then you can look at kind of like how diagonally dominating the distribution is or something like that. I can see how you can check what the network thinks it knows. But if your joint task is over not the same image but different samples, how do you extract what the network knows and doesn't know then?
Yeah. I think you're raising a really good question, and kind of what you're saying is I'm going back here, but pretty much have a paper that's just about that, or a few. I'm going really all the way back. This number 3 here is a bit like that. It's about some of these issues you're raising. But I think the answer that we would do is basically, if we want to know that, the joint prediction we would make is by asking it, hey, predict this same thing multiple times, right?
But wouldn't it produce the same marginal multiple times?
It would produce the same marginal, but not the same joint.
But I mean, wouldn't the joint just be that same marginal copy over?
No, because and that's kind of the what's possible. It can either be the same thing copied over, right? In which case it's aleatoric like this, or it can be this more diagonal thing, as you say. And the reason is from basically this, right? And it's that if the network has some kind of structure such that the index z, right, really strongly influences the predictions, right, then we'll say it doesn't know stuff. It knows it doesn't know stuff.
So could you maybe think of z as slightly perturbing your sample?
Yeah.
And seeing how robust
Yes.
the outcome is?
Yeah, exactly. So basically z, way I think about it is like z is this, you're letting the neural network model kind of its own beliefs, right? And the idea is z is in the space of your beliefs, right? Which could be this 30-dimensional, space, pretty big, right? But not huge. And then you'll say, hey, if my belief is here, what do I think? If my belief is here, what do I think? And if for all the different z's you think the same thing, then that's called being certain. And if for different z's you think different things, that's called being uncertain, right? That's the idea. Yeah.
Sorry if I missed this earlier, but where in the training regime do you guys sort of prevent the node collapse where it just ignores?
Yeah, so that's really the good. So, okay, in some situations, I think you might want to add in like a bootstrapping or some type of perturbation to the loss function, right? But the results I showed you today didn't do that. The results I showed you today didn't, this loss looks like it doesn't really depend on Z, right? But the way it's through this thing, the randomized prior function, because we basically initialize the network with some prior functions that do depend on Z, right? And so now the trainable part of the network has to kind of learn to undo that, right? And so at data, similar to these pictures, this is what this is meant to show, right? And you meant to imagine viewing this ensemble of 4 networks as your uncertainty. So it's like, if I look at any one of these data points, no uncertainty, right? They agree totally. Each one of these samples agrees on each of these, right? And you could imagine, you want to imagine these are like, I could make a 4-dimensional, linear combination of them. But even here, this one like kind of slopes down, right? And this one kind of slopes up. So when you look at the interpolation between these two, it says, hey, there's a bit of uncertainty there, right? But no uncertainty here, and loads of uncertainty out on the left here, because this could be really high, it could be middle, or it could be really low. And that's basically the key thing. And so this paper is about using these in conjunction with an ensemble, right? Because you have a different prior function for each ensemble particle. And then we say, hey, well, an ensemble is just a type of ENN, right? And why should you learn each particle completely separately? Why not learn them in a smoother way with this index?
There's a question from Zoom. It says, for neural bandits, have you compared to Bayes by backprop?
Yeah. And so Bayes by backprop is on there. It didn't do that well. So, it's not there. Okay. Why is Bayes by backprop not there? Because I actually did really, really badly. But it was kind of unfair because all of these other models are trained on the same loss, and Bayes by backprop is maybe meant to have a different loss. So we didn't know exactly how to tune it, and so we left it out of this, but it didn't do well. But yeah, that was why. But we do have the results, but they were so bad, I felt like, so all of these agents are just trained on, mean squared error with some L2, or not mean squared error, softmax, cross entropy. But the prior is really important in Bayes by backprop, so we're like, oh, that's unfair. They have an elbow. Yeah.
Can the approach help with cases of extreme class imbalance, where the Z can help remedy very underrepresented classes?
That's what we were hoping for, and we have ongoing work, which we should actually be able to get up pretty close on some of this OOD work. I think it helps, but the truth is to really, really do well on that, I think you need something a little bit extra than what I've shown you today. And so have some ideas, but I think that I don't think we have like a great solution. It helps a bit, but I think you need something more than what we've got at the moment.
Is that extra sort of having to do with the right prior, or is it?
I think, yeah, if you frame it the right way, you got to have the right prior and you got to have a loss that kind of reflects that. And, you know, I guess, you know, we offered a very simple, the results we've got here have got these specific, you know, losses and stuff. And I think that having either through the prior function or the regularization, you know, you should try and reflect that in your training objective. And at the moment, it doesn't, we don't reflect that. So I think my guess is anything reasonable that adds something like that. Hey, even if you, because this is saying, hey, fit your data that you see, right? But you want to add something that says, hey, fit your data that you see, but also there could be these other classes, you know. And I think if you add something like that, you could make it work.
One more question, sorry.
Yeah, thanks.
So for inference, you like you're done training and you just want to use, you know, like over out of sample test data. Or whatever. How do you? I guess you need to select a value of z, right? So you need that kind of encodes your belief, or can you do it like kind of funny?
Yeah, exactly. So the idea is that, you know, and here I've said, hey, what question are you being asked? And I've said, hey, the question you're being asked is joint prediction. But obviously you could be asked of just one prediction, right? And then ideally the distribution is this integral over all of your z's. And that's like your average, right? But maybe you want to do Thompson sampling like we did in those things. And so then we picked one random z and just did that one sample. But so if you want, basically if you want the average, which is probably what you normally want, or the distribution, do a Monte Carlo, lots of samples of these z's. And that's what we did on Imagenet. But basically, because the Epinet's so small compared to the neural net, the main network, it doesn't end up costing that much. Yeah. So we just forward a lot of them and use that to approximate the integral, basically.
Well, thanks very much,
Yeah.
Ian. Also, thank you to Ham and Anmo for organizing this, as well as I think they're setting up a happy hour for